as a path on the PV diagram. Okay, so for example, what we can look at is we can go ahead and take a look at an isothermal expansion. So we want to look at an isothermal expansion. So iso means that it is going to be the same or constant temp. Well, the temp comes from the thermal part. So the iso means that it's the same temp or the constant temp type of idea for our expansion. And an expansion means that we're going to increase the volume of the gas, that the piston's going to move out, kind of idea. And so then what we can look at is on our PV diagram. We'll go in and put in an isotherm. So there's one isotherm. And so then what would happen is we would start out at some initial volume, some initial pressure, at some initial temperature. And then we're going to expand, so we're going to increase the volume and then end up at this point where the final temperature is the initial temperature. And so then what you see is that the volume increased. This is what makes it the expansion. But you'll notice that the pressure decreases and the temperature stays the same. Okay. Now, if we go in and we look at this, then one of the things we have is that the work done by the gas in this instance is going to be that integral of PdV, which is minus the work done on the gas. Okay. Now, when we look at this picture, the integral of PdV is essentially calculating the area under the curve on the PV diagram. So when we talk about our process, then it's going to move along this curve from here to here. So this is the path that they talk about in terms of our processes. So this is that path. Go from here to here. Okay, so we track it as a path on the PV diagram. And what we're looking at is when you integrate the integral of PdV, then what you get here is that this is our, area under the curve. So this area here is the work done by the gas. This area is the negative of the work done on the gas. These are the diagrams we make, but yet the work they chose is the negative of the area under the curve. Go figure. And so then what we can have is that for an ideal gas, then we actually know how P is a function of the volume if we treat the temperature as being constant. And so then if we go in and put that into our equation, then what we get is we get that our And let me go ahead and write this as the work done on the gas. The one in the book is the negative integral of PdV. And our pressure is nRT over the volume integrated dV. Now, since it's a trapped gas and it's an isothermal expansion, then these are going to be constants. It's almost always going to be a trapped gas. So you can pull those out of the integral. And when we integrate 1 over V dV, then what we'll get is the natural log. And we're going to go from our, initial volume to the final volume kind of idea. Okay. And I probably at this stage should have put that in, that we're going to integrate like this. Let me put in initial volume, final volume, like so. The limits on the integration. Upper limit minus lower limit. Like so. And then what I'm going to do is we can go in and then use our minus sign. So let me go in and rewrite this using a log property first. So nRT, when you subtract the logs, it's the same as dividing. So that's the natural log of the final volume over the initial volume. So now this quantity here, this is the work done by the gas. But if you want the work done on the gas, then you can take this minus sign and essentially distribute it into here and reverse the order of the subtraction. And so then you can hide the minus sign, in my opinion, by writing this as the natural log of the initial volume over the final volume. So notice that it reverses which one's in the numerator, which one's in the denominator inside the logarithm. And so it's really hard to tell the difference between the work done by the gas and the work done on the gas, because really it's just the V over V naught versus V naught over V kind of things.